Okay, let u and v be two vectors in Rn. Which of the following is the projection of v onto u? Okay, so the projection of v onto u, written like this. Oops. So if it's a projection onto u goes in the subscript. If it's the projection of v, that goes here. So this symbol projection u, this part is like a function, and v is the argument to the function. This is u dotted with v divided by the magnitude of u squared times u. And remember, the way I kind of prefer to write this is u dotted with v over the magnitude of u times u over the magnitude of u. And so what this says, remember, this is the scalar projection of u onto v, or v onto u, and this is just the direction vector of u. Okay, it's the vector, the unit vector that is in the same direction of u. And so the absolute value of the scalar projection of v onto u is the magnitude. Anyways, that was a little bit extra. It looks like the correct answer then is A. This is the projection of v onto u. Okay, let's move on to this. So let v1 and v2, these are two vectors in R4. Find a vector v2 tilde such that v1 and v2 tilde are orthogonal, and LV1 and the linear span of v1 and v2 is equal to the linear span of v1 and v2 tilde. Okay, so we can't just find a vector that's orthogonal to v1. We need to find a vector that is orthogonal to v1 and such that v1 and the linear span of the two vectors are the same. Okay, so finding a vector that's orthogonal to v1 would be kind of easy. We could just pick 0, 1, 0, 0, for example. But then that's not going to give you the same linear span. Okay, so the way that you should be thinking about this is you want v2 tilde to be equal to v2 minus the projection of v1 onto v2. Okay, v2 tilde should be v2 minus the projection of v2 onto v1. So the projection of v2 onto v1 is kind of like the part of v2 that is parallel to v1. And so we're going to take that off of v1. And so then all we're going to be left with is the part of v2 that is orthogonal to v1. Okay, so remember that's what we talked about. That was the thing that we talked about in class. That, and we'll actually prove this in just a moment, or do a computation in just a moment to verify this. Okay, but v2 tilde defined this way is orthogonal to v1. So what is this going to be? Well, v2 is 1, 1, 0, 1. Now we're going to subtract off the projection of v2 onto v1. So the numerator is going to be the dot product of v1 and v2. So that's 1 plus 0 plus 0 plus 0. That's 1. The dot product of v1 and v2 is 1. Now we're going to divide by the magnitude of v1 squared, which is 2, times v1, which is 1, 0, 1, 0. And this you get, so 1 minus 1 half. 1 minus a half is a half. 1 minus 0 is 1. 0 minus a half is minus a half. 1 minus 0 is 1. Okay, so if you look at the answer choices, there isn't, this is not one of the answer choices. Okay, however, notice that answer choice C is 2 times this answer choice. Okay, so C is the right answer choice. Okay, why is that? Well, you can just verify by computation that it is orthogonal to v1. The dot product of v1 in this vector in answer choice C is 1 minus 1, which is 0, so it's orthogonal. Why are the linear spans of v1 and v2 and v1 and this vector the same? Well, the vector that I just circled is a multiple of this vector, and the linear span of v1 and v2 and the linear span of v1 and this vector are equal to each other, okay? Because this v2 tilde vector that I just defined here is a linear combination of v1 and v2. Okay, so this shows us that answer choice C is the correct answer choice. Okay, let me just show you that v2 tilde, the way that I've defined it here, actually is orthogonal to v1. I mean, we can just compute it. We can just literally do the dot product of this vector with v1. Okay, but I want to show you the formula. I want to show you based on this formula, which is a little more generic. And of course, we've done this in class, but it's good to just see it again. Okay, so v1 dotted with v2 minus the projection of v2 onto v1. So this is v1 dotted with v2. So I have to divide by the magnitude of v1 squared, which is just v1 dotted with v1, and I multiply this by v1. Okay, so this is equal, so now I can distribute this dot product. So this is equal to v1 dotted with v2 minus v1 dotted with v2 over v1 dotted with v1, and now I'm multiplying by v1 dotted with v1. Okay, now the v1 dotted with v1s, those cancel each other, and what we're left with then is v1 dotted with v2 minus v1 dotted with v2, and so that's equal to 0. Okay, and so this shows that if you start with two vectors, let's say v1 and v2, then v2 tilde defined this way is orthogonal to v1. And this is kind of the principle of what we use to do the Gram-Schmidt algorithm.